exams and you're like totally crazy working hard. And I was inspired by your writing here. The role of the teacher is opening the hidden doors in the student's mind and heart. So I know you're all studying medicine, and I've taught to medical students for many years at University of Chicago before I went to University of Washington. And I know you're very eager to learn about medicine, but what I want to do today is really open the door to fascinate you for science. So I want to talk about the importance of science and in particular the brain science. And this photo is, by the way, from Seattle. So this is the look I have every morning when I go to work, because we live close to the Pacific Ocean. So the brain's most important work is generating time. And I have to turn this all on. And when we think about time, there's one very famous clock in our brain, and that's the circadian clock that determines the 24-hour rhythms every day. You know, like when you are tired in the evening, you're not tired because you work all day long, but because your clock tells you it's time to sleep. When you wake up in the morning also, even if you had a bad night, you will wake up because your clock tells you to wake up. So there's a kind of machine in your brain that tells you when to wake up. But the reality is that this clock sits everywhere in your body. In the liver, in the kidney, in the heart, in every muscle. So when someone like me comes to India, we have something called jet lag. So my clock is now totally screwed up because I want to go to bed now, but it says it's morning. And so now I feel bad, not only because I'm tired, but also my digestive system doesn't work, my heart doesn't work, because it's everything ready to get to sleep. So this is the clock. And in 2017, not too long ago, the Nobel Prize was given for the people that unraveled, that understood how this clock works. And I was very lucky to be present at these Nobel lectures. And they were given to Jeff Hall, Rosbach, and Dr. Young for understanding the molecular biology of this clock. And it was an incredible event and very traditional in Sweden. Now, most people, when they think about timing, they think about this clock. But what I want to tell you today is that, in fact, the brain generates not only the circadian rhythm, but the brain contains a lot of those clocks. So not only the 24-hour rhythm, but in fact you have, while you listen to me, a 30 Hertz rhythm. Those of you that get bored generate a 10 Hertz rhythm. Those that fall asleep generate like a 2 Hertz rhythm. And when some of you fall into a coma because you are so bored, then the rhythm gets even slower. And so when you look at the brain, these are recordings from different areas of the brain. You can see there are everywhere rhythmic activities. This is the hippocampus, which is important for learning and memory. It's rhythmic. This is the amygdala, which is important for fear. And you can see it's also rhythmically active. The striatum, which is important for making decisions. And basic ganglia is also rhythmic. Cerebellum for motor learning, rhythmic, etc. You see everywhere you find rhythmic activity, and also in the neocortex, which determines how you think and feel, etc. Again, there are many, many different rhythms. And the fact is that these rhythms all work together. Okay? So, for example, here the ventral tegmentum and the hippocampus are rhythmically together. And this area, for example, is important for addiction. Like when you become addicted to working, for example, or alcohol or something, then these areas start to work together. Amygdala and hippocampus, when you learn something because of fear, they become rhythmically active together. So you see, these rhythms all work together. But all these rhythms are generated within each of these areas of the brain. So your brain contains a lot of these microcircuits or little clocks. So every area in your brain is a little clock that generates these rhythmic activities. And in fact, We know that they are little clocks because we can take them out. Okay? We can go and take out pieces of the brain, and so you take, for example, in a mouse, a little bit of the cortex, put it in a dish, and now these clocks are working independently. So you take the clock out, and like a watchmaker, and then you have the structure of the cortex. It's a little slice, and this slice will now generate a rhythm that is actually reflecting your sleep rhythm. So what we do in our lab is we take pieces of cortex out and put them into an incubator, and then all these pieces of cortex are sleeping in this incubator. So we have a lot of sleeping cortex in the incubator, and can study, how this activity generates sleep. And so basically, this is just a piece of tissue. And understanding this is very, very important, because every night when you go to sleep, these hippocampal rhythms, so when you have learned something during the day, are rhythmically active with the cortex. And all your memories, everything that you learned during the day, during this lecture, for example, will then go from the hippocampus into the cortex, into the different areas of the cortex, where now you memorize it forever, okay? Hopefully forever. And basically, every night you transfer memory, and we call this memory consolidation, to your cortex, and that's why sleeping is such an important thing. So you learn during the day, and during the night you put it into your brain, into your cortex. Now, understanding this is very important for a clinician. And why is it important? Because there are animal models of Alzheimer, and what you can see is in these animal models, the cortex is very active, but it's not rhythmically active in sync with the hippocampus. So now basically this person is learning something during the day, but then in the night everything gets forgotten because it cannot be transferred to the brain. So there's a problem with generating these clocks. So the clocks are not working together anymore, and that's why these people cannot learn anything. And understanding why they cannot learn anything will help us to eventually heal Alzheimer's disease, because if we can make this clock work like this clock again, then they can suddenly learn something. So understanding science is really important for a clinician. Another example is epilepsy. So this is a recording from an epileptic patient. And what you can see here is you can see all this brain activity, but then in this area here, which is here, then suddenly you can see something starts, it synchronizes and spreads over parts of the cortex. And that's the beginning of a seizure. And so now, again, you see that there's a lot of rhythms here, but these rhythms are so strong that they take over your brain. So in this case, rhythm is bad because it actually synchronizes all over the cortex. And what we can do is now, we can take this piece of tissue out of the brain of these children in this case. And because these children have epilepsy that is not responding to any drug. And so what we do is the neurosurgeon takes this brain tissue out, and in many cases these children have no more problems. Because now this disturbed rhythm generator, this disturbed clock, is not anymore causing any problems in these children. Now, you would like to know, and if we would like to know, why is this clock not working? And so what we do is, once this tissue is taken out of the brain, we put it in a dish, and then this clock will continue to work. And now we can study this and compare this clock with the rhythm of the whole child. And now we can try to understand, why is this clock working so dramatically, and what are the mechanisms? And in many cases it's an exaggeration. In several cases, we were able to find something that blocked this clock from generating the epilepsy. And then we went back to the patient and actually were able to help the patient by taking this clock out, understanding what's problematic, and then going back to the patient. And you will see this in your career very often, that it is an interaction between the clinician who does this and the scientist who does this, and basically the clinician gives the problem to the scientist the scientist tries to solve the problem, goes back to the clinician in order to help this patient. And we call this translational bench-to-bedside research. And that's a very popular, very important aspect of medical sciences. Okay? So, in this case, for example, we identified not only why the clock doesn't work, but we also identified the genetic pathway that is responsible for that. So now we can have gene tools to affect this part of the brain. Now, in the brain there's another rhythm, and this is called the default rhythm or gold signal. It's a very slow rhythm. And this rhythm exists when you do nothing. So let's say, I don't know what happens in meditation, but I could imagine when you really block away every thought you have and just let your brain be active, then this default rhythm comes in. And the default rhythm spreads over the entire brain. But the default rhythm is not occurring exactly at the same time everywhere in the brain. But basically, for example, this area could be very synchronized with this area. This area could be very synchronized with this area. So you can ask the question, how do these rhythms in your brain correlate with each other? So it's a lot of mathematics. So if you're like a mathematic person, then this would be a very interesting project. And in fact, what you can now do is look at the different areas in the brain and see how these rhythms are correlated. And the more they are correlated, the thicker the line it is. So you can say, okay, this area is correlated with this area is correlated with this area. And this is very important because you can make functional networks. You can say, okay, these are connectivities that exist in this particular patient. And then there's another rhythm, which is breathing. And breathing, you think always about the lungs, but the breathing is also an important timing mechanism. So when you look at the prefrontal cortex, which is important for higher brain function, you can see that each time you take an inspiration, this area gets rhythmically active. So what you can see is basically your brain is constantly rhythmically active, and there are rhythms that are interacting with each other, and one of them is breathing. And it's generated by a small area in the brain, which is another clock. Okay? And this clock, we call it the prebursal complex, is generating this rhythm. And like all the other clocks, again, what we can do is we can take it out, or in this case, what we did is we inject toxin in this clock, and then the breathing rhythm stops. So what experiments like this show you is that this clock is actually important for breathing, because when we take it out, you have no more breathing. Okay? But we can go one step further. We cannot just knock it out, but we can take it out. And so when you take it out, you can see this breathing rhythm is still there. So this clock doesn't need the rest of the brain, but it's still generating your breathing. And what's amazing is that this is a penny, an American penny. I don't know how your currency is like, but it's a very small piece of money. And this is the size of this clock. It's sitting here. And we can take it out and now study how does the brain generate breathing. And astonishingly, this piece of tissue generates a breathing rhythm that is very similar to the whole animal. So this is like 0.5 millimeter thick slice with containing the clock, and this is the whole animal, and you can see it looks very, very similar. Now, what's happening in science is we do more and more genetics. And what we do is we use genetic tools to identify nerve cells in this clock. So for example, this is a nerve cell that contains a so-called transcription factor, which is DBX1. It's rhythmically active with inspiration, and you can see it has a fluorescent marker. So basically, we're starting to not only say, oh, this is the clock, but we also try to understand which nerve cells give rise to the breathing. And this is a very powerful tool, because now we can start to ask the question, how do these nerve cells talk to each other to generate a breath? And what we find is that these glutamatergic neurons, they synchronize with each other to form a breath. Okay, so this is basically the origin of your breathing. Now, these genetic tools, however, give you even a new power to unravel, to understand this clock. Because what we can do is we can put in channels, like this is called channel rhodopsin, which is an ion channel that when you shine light on this, a laser light, then it lets sodium in, and this depolarizes the cell. So what you can do is, it's basically like a light switch. You can do genetic tools to put this light switch now in your DBX1 neurons, then you can shine light on and ask the question, what is this nerve cell doing? Or you can do the same thing here, you can inject halorhodopsin or another molecule that now lets chloride in. Chloride is a negative molecule and it inhibits this. So this is a turn on switch and this is a turn off switch. So basically using these genetic tools, we can now start putting switches into single nerve cells to ask the question, what are you doing in this clock? Okay? And when we do this and inject these clocks, these switches into these DBX1 neurons, and we shine light on, you can see now we can trigger an inspiration. So what it tells us is that these neurons, in fact, produce an inspiration. Each time you breathe in, these neurons get activated and make you breathe in. Okay? So this is incredible, right? That you can go into these clocks and understand not only where your breath comes from, but also which neurons are doing this. And what you can do is now put these halorhodopsins in this and shine light on, and now you turn these neurons off and then the breathing stops. So this gives you an incredible tool to understand how this rhythm is generated by the brain. And I want to show you one example why this is incredibly important to do. So these neurons, they release something called glutamate, which is an excitatory neurotransmitter. It excites the network. And so what you have done for many years to understand the role of these neurons is you would inject glutamate into this brainstem area, into the prefrontal complex. So it's an excitatory neurotransmitter. And then if you inject it, you activate all these neurons here, and the breathing goes up. Okay? So your conclusion is, oh, this excitatory neurotransmitter excites breathing. Okay? However, here's the problem. When you inject glutamate into this network, you activate not only these DBX1 neurons, but you activate also inhibitory neurons. So you activate, really, this response is the activation of inhibition and excitation. So you really don't know, is this excitation that you see due to these DBX1 neurons or due to the inhibitory neurons? But of course you would say, oh yeah, it's an excitation, so it must be the excitatory neurons. But now with these tools, what we can do is we don't stimulate the whole network, but we stimulate very specific, only the DBX1 neurons. And so our hypothesis was that now the frequency should go much faster because we now activate only the DBX1 neurons and not also the inhibitory neurons. So that was our hypothesis. And I have a postdoc, Nathan, who did this experiment, and he did this in a whole animal, but also in slices. So he inserted first these light switches into the DBX1 neurons, and then he inserted light to activate the breathing. And here comes science, okay? This is very typical for science. When he did this, the frequency did not change very much. So you can imagine my postdoc was ready to jump out of the window, because all our ideas that DBX1 neurons excite the network suddenly didn't work. And in fact, the first thing he did is check, is the light switch really in these neurons? Does the laser light really activate this? So there was like a half a year of frustration because everything we believed did not work. Okay? But then came another important moment where we realized what's happening. So he then started to activate these neurons exactly when they're active. Okay, so he activated these neurons exactly during inspiration. But now there comes another surprise. In fact, these neurons inhibited the rhythm. So the glutamatergic neurons that we all thought is driving the breathing, in fact inhibits the breathing. And that was like a big shock for us again. But it shows you that basically in these clocks, it depends exactly when these neurons are activated. And you know, with chemicals, you can never find this out, because a chemical just goes everywhere. And so there's a fundamental switch in our ideas how these networks work, because we can now do various time-dependent stimulation. And in this network, I told you there are not only these excitatory neurons, but there are also inhibitory neurons. And these inhibitory neurons are active exactly at the same time that the excitatory neurons are active. So each time, basically, you take a breath, you give the gas, but you also put the brake on. And we never understood why are there inhibitory neurons, because they should block breathing. But in fact, what he found is that in fact these neurons stimulate the breathing. So when you stimulate these inhibitory neurons, you can see how much faster the breathing rhythm is. And so we had to change totally our idea how this clock works. But it was only possible because we could put these light switches on and stimulate these neurons exactly in these phases. And I could talk now for like an hour explaining you exactly why this is, because we worked, like Nathan worked for 4 years on it, but he solved the problem. And we got very good papers out, like in Nature Communications, because it changed how we think about the clock. Okay? But I want to tell you now another rhythm in your brain, which is the sigh. Everybody, you know, who is sad or falls in love or something, you sigh. Okay? When you have an exam in an hour, you look at the exam and say, oh my God, you know, you sigh. But really, the sigh occurs in a very rhythmic fashion. It's another clock. So every few minutes, you sigh. So when you listen to my talk, you know, even if you don't fall in love with me, you will sigh, okay? All the time, every few minutes. And this is the clock, isolated. And this is a child. This is a baby, 1-year-old baby. You can see the clock is exactly the same timing. So basically, there's a clock that generates your sigh all the time. And Liza and Tatiana in my lab, they unraveled the mechanism of this sigh rhythm. And to our big surprise, this rhythm was not generated by the neurons, but it was generated by glia cells. So these glia cells are rhythmically active, and they release ATP, and that ATP activates the network. And in order to show this, again, she used optogenetic tools. So she put in this light switch into glia cells, and you can see that each time she puts a light on, this slice generates a sigh. So again, you know, there are different clocks. One for breathing, that depends on the neurons, and one for the sigh, that depends on glia cells talking to the neurons. So you can see how basically using these light switches now helps us to understand how these clocks generate rhythmic activity. Okay? So the big philosophical question is why rhythms? You know, why is the brain everywhere rhythmic activity? You know? And in some cases it's an easy answer. For breathing it's very clear because you activate your lungs, and if you don't activate your lungs, you have no oxygen and you die. Okay? So the rhythmic activity for breathing is very clear. You have to always provide oxygen. Also for the sighing, why you sigh, it's very straightforward. Pretty straightforward, okay? Because what we can do is again use genetics. We can manipulate the network and put in something that blocks the PQ type ion channel that is important for the communication of the glia and the neurons, and then these animals do not sigh. So we can knock out very specifically the sighing, and they are still breathing but not sighing, and what happens is their lungs get clogged up. And we call this atelectasis because you have to always open your lungs very big in order to make these alveoli that you have open. Okay? And if this doesn't happen, then the lungs gets clogged, and then after a while you get pneumonia, and then these animals die. size. So this shows us the size are important for preventing atelectasis. But when it comes to rhythm, it's not so easy to understand why, if the breathing activates the lungs, why should breathing also activate my prefrontal cortex? You know, the prefrontal cortex is important for higher brain functions. You know, when you listen to me and get hopefully inspired, you don't get inspired because you get more oxygen. You get inspired because it activates your prefrontal cortex. Okay? So this is a very interesting puzzle, because all the physiologists for many, many years focus on the question, why do we breathe to activate the lung? They totally ignored the fact that breathing is also open to the cortex. But India is the leader here. Because in India, you knew for many, many years that actually breathing is important to keep your thoughts collected, okay? So deep breathing is a very important mechanism to keep you focused, for example. And so really, the Indian people, for many decades, knew already that breathing is not only important for activating your lungs, but it's also important for your brain functions. And many times you think it's because it's the oxygen that you bring in, but I don't think it's the oxygen. I think it's this neural drive that puts a timing right in your brain. Okay? And so that gets me to the question, why is your brain rhythmically active? Why is your brain always rhythmically active? And that's where it comes to the talk title. The main role of the brain is to generate time. And what do I mean with this? Okay? Now, when you think about it, when you see a red car driving, okay, you see a red car going fast, what happens is the time your brain needs to process red color as opposed to white color is very different. Okay? So the perception of color takes a certain time. Now the perception of the movement takes another bit of time. It's different time. And it goes also to different brain areas. The perception of the sound that this car produces takes another time. So now you can imagine, you see this car, the movement, the color, the white, the sound, and maybe the smell of this exhaust all comes into your brain at different times. But yet, your brain can bring all these different processes that come in your brain at different times to make one event that is simultaneous. Okay? So if the brain wouldn't be able to do this, you know, this red car would move away, the red color would come way behind it, and then sometimes comes the smell. So your brain has to actually generate simultaneously. So everything you see outside in the world, your brain takes apart, puts it into different areas of the brain, and then puts it together again in order to make one coherent message. So when you drive the car and you have no clue how the snow works, maybe, unless you went to the Himalaya, but this is a typical situation in Europe when it snows. This car basically stopped, these cars are driving, so your brain has to realize very, very quickly that this red color is not moving, whereas this red color is moving. So you have to immediately interpret movements and what is not moving in order to react. So your brain really depends on creating the simultaneously to know what's moving together, what's not moving together. And this is a huge task. And so what I basically showed you is that the real world outside needs to be disassembled into its own, in its parts, you know, the acoustic part, the visual part, the movement part, and then it has to be put all together. And in the wake state, so while you're listening to me, all these activities, of course, come in at different times. So when you stick an electrode in your brain, it looks like this, okay? So it's not synchronized, it's nothing rhythmic. So you can see all this activity, because, you know, like visual information comes in, sound information comes in, smell comes in, everything comes